supernovae. So one example of a lens supernova you can see right here on the slide, which is supernova Zwicky. And here you see 4 dots of light, which are 4 copies of the same supernova. Another example is this one, supernova Requiem. Here you see 3 images of the same supernova within the white circles. And actually, a 4th image is predicted to appear somewhere around here in 15 years' time from now. So in this seminar, we'll go over the physics behind these weird optical effects and also how we can use them to learn more about the universe. So we'll explore the state of the field of lens supernova discoveries and dive deeper into one particular discovery of supernova Zwicky. And then we'll look ahead to the future, where upcoming telescopes are predicted to discover orders of magnitude more lens supernovae than we currently have, which will completely transform the field. But let's start. How do we create a lens supernova? So if we have an observer and a distant supernova explosion, then in very rare occurrences, there is a massive galaxy or galaxy cluster located along the line of sight. And this can act like a gravitational lens. So it bends and magnifies the light rays coming from the supernova, such that the light goes in multiple directions around the lens galaxy, and the observer can see multiple images of the same event. Now, this doesn't only look spectacular, but it's also really useful because it can give insights into a wide range of science topics. So first of all, as I said, these objects are very rare because getting this exact alignment in the universe doesn't happen often. So from the search for lens supernovae, we can learn a lot about big data searches in general. And then when we finally discover these events, by looking at the background source, we can learn a lot about high redshift supernova physics and galaxy evolution. By looking at how the light is distorted by gravity, we can learn about gravity and also about dark matter in the lens galaxy. And finally, when we add all of this together, we can even learn about the universe itself, cosmology. Now, more concretely, how does this work? If we want to do cosmology with lens supernovae, we need 2 ingredients. The first one is the time delay between the appearance of the multiple images. So as I showed before, supernova Requiem had 1 image pending in 15 years from now. Usually the time delay is a bit shorter, but since the light rays travel along different paths to each image location, we will also see them appear at different moments. And by studying the brightness of the object, we can actually measure this time delay. The second thing we need is knowing the gravitational potential of the lens galaxy and also some of the structures along the line of sight. And if we combine these things together, we can infer absolute distances to the lens supernovae, and with that, we can calculate the expansion rate of the universe, or the Hubble constant. And this is especially useful because currently there's a persistent tension between 2 methods to measure the Hubble constant. So this so-called Hubble tension relates to 2 different ways how we can measure the expansion rate of the universe. The first one is by looking at the first light we can see in the universe, the cosmic microwave background radiation. And then by looking at the characteristic scale of the fluctuations, we can determine the distance between us and the CMB. And if you use a cosmological model, you can convert that distance into the expansion rate of the universe. The second is the local methods, where you relate distances and redshifts of nearby objects to get the expansion rate of the universe. And this one usually uses the so-called distance ladder, where you link the nearby calibration to nearby objects to ones further away, and so on. So the leading results from these 2 measurements are a Hubble constant value of 67.4 from the Planck collaboration and a higher value of 73 from the Schuss collaboration, which uses Cepheids and type 1a supernovae. And these 2 are now in 5 sigma tension with each other. So it's really a big open problem in cosmology. And gravitational lensing is really useful because it provides us another way to have a local measurement of the Hubble constant, where you don't have to use the distance ladder because you immediately infer absolute distances to objects that are far away. And for this purpose, gravitationally lensed quasars have already been used by the Holy Cow collaboration. So here you see a result where they used 6 lensed quasars to infer the Hubble constant. And the resulting value, 73.3, is very precise, and it agrees with the other local measurements that I showed before. Okay, so maybe we're done here, right? Well, not quite, because there are a lot of challenges involved in using lens quasars for cosmology. So first of all, it's really difficult to accurately constrain the mass model, and there are degeneracies involved that are hard to get rid of. Another thing is that it's difficult to expand the sample we have of lensed quasars for cosmology, because if you want to measure the time delay of a lensed quasar, you typically need to monitor it for a very long time, sometimes decades, or you need really high cadence observations. So, okay, that's difficult with lensed quasars. How about lensed supernovae then? Because this idea of measuring the Hubble constant with gravitational time delays was already proposed in the 60s by the Norwegian astrophysicist Sjur Refsdal. And when he proposed it, he actually envisioned to do it with lensed supernovae. And lensed supernovae have several differences and also some advantages over lensed quasars. So some of them are that lensed supernovae, especially certain types, have well-defined light curves that we know a template for, and also typically they have shorter time delays. So it means that you don't need to monitor them as long, and you also can get away with having fewer observations. That makes it easier to expand the sample that you have. Secondly, when a supernova fades away, I mean, this is a bit of a curse and a blessing, because of course it means you have to catch it before it fades away. But when it does, it allows you to study the lens and the host galaxy in more detail. For quasars, this is a problem because the quasar is always there, it's very bright, and often it outshines the host and lens galaxies. But there's a lot of information there. So you can use that to constrain better the mass profile. And if the supernova is of a type 1a, it's a so-called standard candle, so it always has approximately the same brightness, which means that you get an additional constraint on the absolute magnification, which also helps to constrain the mass model. And finally, a nice bonus is that you can use them to learn about high redshift supernova physics, which is also useful for cosmology, because type 1a supernovae are typically used for the distance ladder approach, and this assumes that high redshift type 1a supernovae have the same properties as the low redshift ones. Okay, so these are some advantages, but of course the main challenge when you use lensed supernovae is that it's very difficult to find them before they fade away. And after this idea was proposed by Sjur Refsdal, it would take another 50 years before the first multiply imaged lensed supernova was discovered. So this is supernova Refsdal, named after him. And it was discovered in this image from the Hubble Space Telescope of a galaxy cluster. So just to get an idea of the audience, who of you has seen this image before? Raise your hands. Okay, a few, of course, but not everyone. Good. Yeah, there's a lot happening in this image. So we have the more yellow-orange galaxies. This is the foreground cluster that acts as the lens. And then you see the bluer galaxies, star-forming galaxies, which are behind them. Let's zoom in a few important regions here. So in 1.1, this cut out. Let's zoom in a little more so you can properly see it. So this blue galaxy is behind the galaxy cluster, and a supernova goes off in the galaxy that creates 4 red dots, which are 4 images of the same supernova, which is being lensed by this foreground galaxy here. So that's already amazing. This was the first lensed supernova discovery, sort of made by accident. But it goes even further, because what also happens here is that the host galaxy of the supernova, this blue galaxy, is actually imaged multiple times as well. So you see the same galaxy in 1.1, 1.2, and 1.3. So if the supernova goes off in this galaxy, of course it should also appear in the other images of the galaxy at some point. So then people constructed the mass model of the galaxy cluster, which is indicated by the white lines. And they predicted that supernova Refsdal had already appeared in 1.3, but some time ago, so we missed it. But it would reappear in the galaxy in 1.2, 1 year after this observation. So, of course, everyone was ready 1 year later to take follow-up observations. And exactly as predicted, supernova Refsdal reappeared. So this was amazing. It's a good test for the lens models, but it also means that you have an accurate time delay measurement because you know when it appears 1 year later. So using these measurements, this led to the first determination of the Hubble constant using lensed supernovae. So it has a value that's compatible with the CMB measurement. The uncertainties are still quite large, which is mainly because of the complexity of the, of the mass model of the galaxy cluster. But it's still amazing that for one object, you can have this measurement already. Okay, so that was supernova Refsdal, the first one. But afterwards, we have discovered more lens supernovae. So I'm going to show them here in this diagram, where I will show them in terms of the redshift of the supernova and the maximum time delay between the images, because these are important properties. Okay, so let's go. We just go through the discoveries a bit quickly. Supernova Refstal, then we had IPTF 16G EU, which unfortunately didn't get a nice name. Supernova Requiem, C22, Supernova Zwicky, Supernova Hope, and finally, Supernova Encore. Okay, so these are the ones we have now for which we can measure the redshift and the time delay. And there are multiple interesting things if you look at this plot. So first of all, you see that Supernova Requiem and Supernova Encore look very similar, right? That's because they're actually lens supernova siblings. So it's two different supernovae that went off in the same host galaxy and were lensed by the same galaxy cluster. I mean, what's the chance of that happening in such a small sample? But it did. And then another interesting thing about this plot is that you see there's such a wide spread in time delays, really ranging from a few hours to a few decades. So this really shows the variety of these systems. This depends a lot on how massive the lens is and what the configuration is, how much symmetry you have, and so on. Another thing that's visible here is that you have sort of two populations, which I indicated now with red and blue objects. So these populations correspond to lens supernovae that are lensed by galaxy clusters in blue, or where the lens is a single elliptical galaxy in red. So the ones that are lensed by clusters, the cluster scale lens supernovae, they have all been discovered by the Hubble Space Telescope and the James Webb Space Telescope, because they just survey known galaxy clusters, and then there you discover new objects appearing, which are these lens supernovae. So that's also why they have a higher redshift typically, and they have large time delays because the masses of the clusters are so big. And we've seen that for supernova Refstal, we've determined the measurement of the Hubble constant, consistent roughly with Planck. And we have a second measurement of the Hubble constant from lens supernovae, which is from supernova Hope with H0 PE. And this is 75, consistent with the other measurement of the local one. So we haven't really solved the Hubble tension yet with lens supernovae, but we're getting there. And it's exciting to see that the first measurements are now coming in. Then for the galaxy scale lens supernovae, we found two so far. Both of these have been discovered with survey telescopes. So you scan the entire sky looking for new objects, but these telescopes, they look very wide, but they cannot look very deep. So the ones that you find are at lower redshifts. And currently we're sort of at the limit of where we can discover lens supernovae. This will change with upcoming telescopes, which will look deeper into the universe. So it's really exciting. We're expecting to find many more with these missions. And this is what I'll talk about at the end of the talk. But first, I want to focus special attention to Supernova Zwicky, because this is the one where I was part of the discovery team in Stockholm, and it was really exciting. And also Supernova Zwicky is very interesting because in many ways, it's at the extreme ends of the properties of lens supernovae. Okay, so Supernova Zwicky was discovered with the Zwicky Transient Facility, a telescope in California that, as I said, scans the entire sky looking for new objects. Well, how do we find these newly appearing objects, these transients, when we have so many objects in the whole sky? We do this by having reference observations and then subtracting them from new observations. So you get a difference image and you see everything that's either new in the sky or that's varying in brightness. So in this way, we find a lot of objects, and we're actually a very big collaboration with many partners in different places on the world. And everyone is interested in doing different things and different science goals with the Zwicky Transient Facility. And in Stockholm at the Oskar Klein Center, we're the ones looking for the lensed supernovae, which is very difficult because we only expect to find a handful per year at most. And we also partner up with collaborators in Berlin to do this. But we got lucky at least once, and we managed to find a lens supernova with ZTF data. This was supernova Zwicky. So now I'll go over the discovery story of supernova Zwicky, and I'll do that with a zoom in, where we start from the wide field of view of ZTF, and we're going to zoom in all the way using data from different telescopes until we finally see the resolved images of supernovae Zwicky. And along the way, I will talk more about what led to the discovery and what made us alert to the fact that it was a lens supernova. Okay, so here we have the quadrant where we found supernovae Zwicky. And initially, it was just one of the many objects that we got an alert for. It was called ZTF22AAYLNHQ. Nothing particularly special. Also, when we looked at the light curve, this is usually how we assess objects. We look at how their brightness is changing over time. It looked kind of a standard example of a supernova where you have a rise and then a slower decline. The only thing about this object was that it was quite bright, and it was actually bright enough to get an automatic spectroscopic follow-up observation, because we do this for the brightest objects such that we can have a complete sample. So we got a spectrum for this object, and from that we can learn a lot about what type of transient it is, what type of supernova, and at what redshift. And for this one, the best fit was a type 1a supernova at a redshift of 0.35. I mentioned type 1a supernovae before, which are the standard candles, so they have approximately the same brightness. And with the Zwicky transient facility, we never see them up to a redshift of 0.35. What we actually see is maybe up to redshift 0.10, but never more than 0.15, because when they're further away, they're just too faint for us to see with this telescope. But now we have this object here all the way at redshift 0.35, which also appeared really bright to us. So in order to explain this, it has to be magnified around 24 times. So this, of course, was a smoking gun signal that we are dealing with a gravitational lens here. So we got really excited. We baptized it into a nicer name, supernovae Zwicky, which is named after the telescope, but also Fritz Zwicky, because I think he coined the term supernova, and he also was the first to suggest that whole galaxies can act like lenses. So it's quite a fitting name. So from this moment, we got really excited. And of course, we had to get more observations because we want to study the supernova itself, the lens galaxy. We want to resolve the multiple images of the supernova, measure the time delay, get the expansion rate of the universe, and ultimately solve the Hubble tension. So to do that, we had to have deeper observations. And the first ones we got were from the Very Large Telescope in Chile, where here you're starting to see a bit more details of the field. But this object here is supernovae Zwicky. It's still quite difficult to make out the details. Then we went deeper with observations from MUSE, also on the VLT. And these observations are incredible because every pixel here is actually a spectrum. So from this, we could learn a lot. And you're starting to see more details here because you see the red blob, and next to that, the larger blue blob. So when we looked at the spectra of each of these, we saw that the red one was a galaxy at the same redshift as supernovae Zwicky. So this had to be the host galaxy of the supernova. The blue blob, we saw signals of the supernova at that redshift, but also signatures of another galaxy at a lower redshift, which had to be the lens galaxy. So this blue blob over here is a combination of the supernova images on top of the lensing galaxy, all blended together. So still, we were not able to make out the separate images here. And at this point, we started to get a bit worried because this is already one of the best telescopes in the world. So maybe it was just not possible to see supernovae Zwicky. Maybe it was just too small. But then we got observations from the Keck telescope on Hawaii. And here you see actual video of the night that the observations were taken. So this is the Keck telescope pointing a laser into the sky, observing supernovae Zwicky. And the laser is to do adaptive optics. So this is where you measure the distortions of the atmosphere on the laser. And then you have the mirror of the telescope that can correct in real time for these distortions, which make you have really sharp images from Earth as if you were in space. It's quite crazy. So this was a bit our last hope. So yeah, let's have a look. What did we see? So here, finally, we saw supernovae Zwicky with all the nice details. We see 4 images here corresponding to one supernova. And you see a bit of light here in the middle, which is the lens galaxy. And then here you see the center of the host galaxy, which you already saw before was a bit offset. So this means that the supernova didn't go off in the center of the host galaxy, it went off a bit towards the outskirts, which is not uncommon. But that meant that the supernova was behind the lens galaxy, so it was strongly lensed, but the host galaxy itself was not strongly lensed. Interesting configuration. Yeah, but this was amazing. So we had these observations from Keck, and then a few days later, we also got observations from the Hubble Space Telescope with the LensWatch collaboration. Here you also can see the multiple images of supernova Zwicky, and we got observations in multiple filters, so we could also study the colors of the supernova. And getting these observations was amazing, not just because you finally were able to see the different images, but with this, we could also start to do our analysis. So we determined the typical size of supernova Zwicky, the Einstein radius, which was 0.17 arcseconds. And this is incredibly small. It's one of the smallest lens systems discovered in the optical. And we could also determine the stellar mass of the lens galaxy, which was around 10 billion solar masses. And this is actually extremely light for a lens galaxy. So we were surprised to find this result. And to put that a bit in context, comparing to other lens galaxies out there, so here I'm showing a population of lensed quasars and lensed galaxies in terms of their size, Einstein radius, and their stellar mass. And you see that supernova Zwicky and also 16 GeU, which is the other galaxy scale lens supernovae, really are outliers. So they're part of this new population of low mass lens galaxies that we could only discover because they happen to be lensing a standard candle. That's why we knew it was a lens and did all these follow-up observations. So it's really cool that we're starting to see this population. And they also have particular properties. So both supernova Zwicky and 16 GeU were discovered because they were so highly magnified. And this is something that you get if the supernova is right behind the lens galaxy. You get a lot of magnification. But this also means that the time delays are typically very short because you're so symmetric. And you can see that already when you look at the light curve of supernova Zwicky. And this is the unresolved light curve. So it's the light curve from all the 4 images summed together. You already see that it kind of looks like a normal supernova light curve. There's not really any signature that some of the images are offset in time when you would see a bit more of a bump. And when Anna did these fits, she fitted 4 light curves to this total light curve. And she found a best fit time delay of less than a day, around 10 hours, which is so short. And it's really remarkable to think that you have a supernova, light from the supernova travels 4 billion years through the universe. It takes different routes around a galaxy, and then it arrives on Earth with less than a day difference. That's how symmetric the system was. But it's also quite inconvenient because if we want to use supernova Zwicky to determine the Hubble constant, then we need to have a measurement of the time delay, which scales inversely with the Hubble constant. So any uncertainty you have on the time delay will also translate into an uncertainty on H0. And then since we have observations every 2 or 3 days, we have now uncertainties of around 2 or 3 days on this measurement, so the precision is very low. And something similar was the case with 16 GeU, which had a time delay of 1.5 days, also incredibly short. So these systems, these galaxy scale lens supernovae that we have so far, can we use them to calculate the Hubble constant? Well, I did sort of try that, of course, just for fun. And this is what I got. It's so you see that because the time delay is consistent with 0, the values you get of the Hubble constant also have this wide tail going towards really high values. And if you then plot over the leading measurements of the Hubble constant from the CMB and the local measurements, then you see that supernova Zwicky is not going to do anything to distinguish between those. So it's not going to solve the Hubble tension. But that's okay, because we can use them for other things. For example, to learn more about high redshift supernova physics and about lens galaxy substructures. Because something interesting is happening when we compare the observed fluxes of the images with the ones that we get from our best fit lens model. And this lens model is constructed making a gravitational model for the lens fitting to the image positions of the supernova. And you see that we predict image A to be the faintest, but we observe it to be the brightest. And similarly for image C, we also need some additional magnification compared to our model predictions. So this led us to conclude that this simple, smooth model that we were using for the lens galaxy was not accurate enough to describe reality. And instead, you need something with more complexity, such as additional effects from microlensing, which are lensing effects from stars and other compact objects in the lens galaxy that also contribute to the magnification. And because the distribution of stars and compact objects can be different for each image position, this will allow you to get different magnification for each of the images. So this is very interesting, and we're looking into this further. And another thing you can do is study high redshift supernovae in a lot of detail. Because the supernova is so magnified by the lens galaxy, you can get a really high signal-to-noise spectrum of this high redshift supernova that actually has comparable quality to supernova spectrum from really nearby. And when we compare these two, we see that supernova Zwicky is very similar to other type 1a supernovae at low redshifts. So as I said before, this is an important cross-check for cosmology, because when we use type 1a supernovae for cosmology, we do also assume that the high redshift population is similar to the low redshift one. Okay, so going back to all the lensed supernova discoveries, we've now had a closer look at two of them, the galaxy scale lensed supernovae 16GU and supernova Zwicky. And we saw that they're quite peculiar and they share a lot of the same properties. Both have a really light lens galaxy, they're really highly magnified, have short time delays, so they're not great for cosmology, but we can use them to learn about lens galaxy substructures and supernova physics. But as I said, these guys are sort of extreme objects that we only find because they were so highly magnified. And they are probably only the tip of the iceberg. And this is indicated by simulations that PhD student Ana Caracedo did, where she simulated the lens supernovae that we should be able to detect with the Zwicky transient facility. So here you see how many we expect to find in the full 5-year duration as a function of their brightness. And she predicted that if you only look at the brightest objects, like supernova Zwicky, then indeed you expect to discover around 1 in the full duration of the survey, which is also what we did. But if you look at the fainter objects, then there should be a handful more lens supernovae in the data that we haven't found yet. And these are probably systems that are less highly magnified, but therefore also have longer time delays because they're not so symmetric. So these are ones that could be more useful for cosmology. So of course, we want to try to find these, the ones that we missed. And this is a project that Alice Townsend did, a PhD student at Berlin. She went through archival data of the ZTF for the past 3 years. And she applied a lot of different cuts based on redshift information and information about the transient, but also the galaxy it was associated to. And after this extensive search, she narrowed it down to 2 objects that look quite promising. So these ones pass all of the cuts that we have. They have spectroscopic redshifts of around 0.2, which could correspond to the lens galaxy. And their light curves are actually better fitted with several supernova light curves than with one. So here she fitted 2. And if these fits are correct, then they have time delays of the order of 20 and 30 days, which is what you would expect for these objects. And it's also a good time delay to do cosmology with. So that's very promising. Of course, these objects, they're not there anymore. So we may never really know if they were lensed supernovae. We can try to go back and see if the host galaxy is lensed and so on. But it may still be hard. But methods like this are incredibly important for the future as well, to make sure that we don't miss any lensed supernovae. And this will become especially important in the next decade, when we have upcoming telescopes like the Vera Rubin Observatory that will conduct the LSST survey. And this is a survey that will scan the southern sky, but looking deeper and in more colors. And expectations are that LSST will discover a lot more lens supernovae than we currently have. So that was the motivation for this project that I did within the Dark Energy Science Collaboration, where we wanted to answer questions like, how many lens type 1a supernovae will LSST discover? What are their properties? And how can we distinguish them from unlensed supernovae? So to do this, we simulated realistic lensed supernovae, including microlensing effects, and we computed their light curves, and then applied the simulated observing strategy of LSST to see whether these objects were still detectable or not. Putting that all together, Putting it together, our results for the lensed supernova detections with LSST is that we expect to find around 44 lens type 1a supernovae a year. I mean, this is really great if we compare it to what we currently have. It means almost one lens supernovae a week, which is kind of crazy. But of course, not all of these will be useful for cosmology. Some will have shorter time delays, like supernova Zwicky. But if we look at the subset of those with time delays larger than 10 days, we still expect to find around 26, which is really good. We also looked at how to separate lensed and unlensed type 1a supernovae. And we did this based on their peak magnitude and their colors. And here you can see that you can obtain a partial separation because lensed type 1a supernovae are brighter and redder than unlensed type 1a supernovae. So even though you will both see them out to high redshift with LSST, lensed supernovae will appear redder for that certain color, for that certain redshift. And then we also made a subset of our detected sample, which we call the gold sample, which are promising for follow-up observations. So we selected the objects that had a long enough time delay, were bright enough for follow-up, and had enough early detection so that we can have time to trigger the next observations. And this gold sample amounts to around 10 objects per year. And if we assume some uncertainties in the mass model and time delays, which are similar to previous literature analysis, then we could get a precision in the Hubble constant of 1.5% in only 3 years of LSST observations. That's great. Of course, this is more of an upper limit because undoubtedly we will miss some of these objects or we will not get the required follow-up that we need. But it's still a very promising result for such a new probe. It also means, though, that it's really important to be prepared. So we need to find these objects as soon as possible and trigger follow-up observations. And these preparations we are mainly doing within the science collaborations and topical teams of the Rubin Observatory. So I'm the co-convener of the Strong Lensing topical team, and we work together a lot with the Strong Lensing science collaboration to really prepare for the upcoming data. So I won't bore you with all the details, but just give you a little flavor of what are activities that we do. So this involves, for example, creating realistic simulations that every user can run in order to test their own lens finding methods. We also organize search challenges within LSST, both to find static lenses and to find transient lenses. And our idea here is that we want people to collaborate. So it's not really a competitive challenge, but we want them to see how many lens supernovae, for example, can we find together with our lens finding methods. So we're not going to pick one standard lens finder because we believe that every lens finder is sort of good in their own thing. So if you combine all of them together, you can have a larger population of lensed supernovae. We also use the simulations to make cosmology forecasts to see what we can expect from lensed supernovae. And this we also combine with other cosmological probes to see what the joint precision is that we can achieve with LSST. Then we coordinate follow-up resources, both internally, but we also apply for time at the Hubble Space Telescope and James Webb Space Telescope. And we have dedicated databases for strong lensing, which a lot of them seem to be inspired by cats. And the idea here is that we have our own databases such that we can store all the observations and the metadata that we need. Another important thing is that we need to have fast methods so that you can make predictions and also update these predictions as new data comes in. And with traditional methods, this is difficult because it takes long to run a lens model and to infer the time delays. So this is where machine learning can be quite useful. And this was a project that I did with my master's student, Gonzalo Gonçalves, where we created a machine learning pipeline to infer the Hubble constant from lens supernova image time series. This was done with simulated data from the Roman Space Telescope, which is another upcoming mission. And here we have several different convolutional neural networks that each predicts different lens parameters and time delays. And then we add those together to get the final estimate of the Hubble constant. We also use simulation-based inference to get full posteriors. And here you can see that if we have many systems, we can recover the input value of H0. Of course, this is also a bit of a pessimistic estimate because this is not taking into account any follow-up observations that we need to get for these systems. But it's also useful because here you can assess the uncertainties related to each parameter, which can then give you an idea of what data you need to get in order to improve the final precision in H0. So it can therefore help with follow-up strategies. And as a side note, Gonzalo is currently looking for PhD positions, and I can highly recommend him. He's done really great work. So to summarize, gravitationally lensed supernovae are extremely rare, but in the last decade, we finally started to detect them. So we have 7 discoveries here so far, of which we found supernova Zwicky, which also points to a new population of low-mass lens galaxies. And in the very near future, our telescopes will be powerful enough to look so deep into the universe that we can discover dozens and even hundreds more lens supernovae. Predictions I made for LSST predict that we will find around 44 lensed type 1a supernovae a year. And with this sample, we can get really accurate measurements of the Hubble constant. We can learn about substructures in lens galaxies, high redshift supernova physics, and who knows what more. Thank you so much.
So thank you, Nikki, very much for this beautiful talk. Do we have questions or comments in the audience?
So for the determination of the Hubble constant, I'm wondering, you mentioned time delays and mass distributions. What is the one single biggest systematic uncertainty? And if you have several different supernovae, right, and you're trying to combine that information to get the Hubble constant, are there any systematics that could affect all of them in the same way, right? So I'm trying to understand what is the limiting factor here.
Yeah, it's a sharp question. It's definitely in the lens modeling, because the time delay is kind of easy to measure if you have good data. You don't need to assume a lot of things. You can even do it without assuming the shape of the light curves of the supernova. But the mass distribution is difficult, and often people do assume functional forms for this mass distribution, which can be too simplistic. Another thing is to take into account all the structures along the line of sight, which is also hard to do. So yeah, that's definitely the main challenge.
Thank you, and thank you for the talk.
Thanks, Nikki. Very nice results. I'd like to ask you about the simulations for LSST. How do they differ from the Daniel Goldstein's ones a few years ago in terms of predictions and in terms of the modeling?
So the main difference here is that they only used limiting magnitude cuts to get a rough idea, but we implemented the full observing strategy. So that means that, yeah, you're going to miss out on more of the lens supernovae. But other than that, it's very similar to the paper from Radek Wojtek, where we combine both of the discovery methods, image multiplicity, but also magnification methods. Whereas Danny Goldstein only looked at the magnification method, so you can find really bright objects. But we also took into account that even if they're not very highly magnified, but you can sort of resolve the multiple images, then we also find them. So our results would be a little bit higher than what he had, but comparable to Wojtek.
And in terms of numbers, rates per year?
Yeah, I think, so the main thing is that the rates per year were very high if you look at the total number of lens supernovae, especially because of type 2N supernovae, which are predicted to be very bright, so you can see them with their high redshifts. So then they got rates of several hundreds a year. If you only look at the type 1a supernovae, Radek Wojtek predicted to find around 80, 90. So we have roughly half of that. So those numbers get halved a bit because if you take into account the observing strategy. But we didn't do this yet for type 2N supernovae. And that's also very uncertain because we don't really know much about type 2Ns and what they look like and at high redshifts and so on.
Okay, thanks a lot. Yeah.
Any more questions? Actually, I have one regarding the separation. When you have systems with short time delays, you mentioned that they are not useful for determinations of H0, but they are useful to calibrate your model of the lens galaxy or the lens. How is the opposite? I mean, if you have a strong, long time delays, these systems are also, besides of H0, are also useful to actually to calibrate your and to improve your mass modeling, I guess, no, with the data you collect.
Yeah, also in a sense. So if you have longer time delays, you typically have that for double systems with only 2 images instead of 4. Of course, it's nice to have 4 images if you want to learn about the lens galaxy, because you probe it in more directions, more points. Another advantage of these really low mass lens galaxies that are very symmetric and highly magnified is that the images form very close to the center of the lens galaxy. So if you want to understand more about the structure in the center, that's useful. Whereas the ones with larger time delays typically also are a bit larger, so the images form a bit further away. But I think it's also useful to have this whole range of systems so that you can have several lens supernovae where each of them probes a different part of the lens galaxy. And if you add that together, you can learn about the galaxy as a whole.
Okay, thank you. Any more questions?
Yeah. So how well can you constrain the structure of your lens galaxy? So for example, can you distinguish between different dark matter profiles or the sort of inner morphology of the galaxy?
Yeah, that's something that we're working on now. So it depends on a lot of things. Sometimes, like for Supernova's wiki, it's a bit difficult to have an accurate lens model because you don't have the host galaxy, lens in an arc. So you only have 4 positions of the supernova. That's not a lot of information, so it already makes it difficult to constrain the slope of the lens profile. However, then you have the standard candles, also like Supernova's wiki, and this gives you absolute magnification, which then in turn constrains the slope. So using that information, you can still learn about these models. And what we're looking into now is if we can also convert that into an NFW profile and learn more about the dark matter in that way.
Thanks. Great talk.
Any more comments, questions? Online, anybody wants to ask something, anything to? I don't see any hand. So if not, let's thank Nikki again for her beautiful talk. Of course, after all the students come by to actually to take your participation, we can all reconvene in the scientific coffee in the cafeteria. Okay, thank you. Sí, yo no, no, no,